y equals, let's say 100. Let's just use what we were just doing in word problems. Is that an increasing or decreasing word problem? Exponential. It's decreasing. Why? Because what's less than 1? The b, right? So you said that this is decreasing because that's lower. It's between 0 and 1, someone else said, which was completely correct. What is it decreasing by? What percent? 12%. It's how far away it is from 1. Okay, what if I give you this? Increasing or decreasing? Can you put your feet in your desk? Yeah. Increasing or decreasing? Increasing, but why? It's greater than 1. Okay, so increasing by what? %. We got there eventually. By 1.3%. How do I get the percent? Just take the 0.013 and times it by 100. So it's increasing by 1.3%. What if I give you this? Increasing or decreasing? Increasing by what? 1, which would be how much percent? 100. And the reason why is if I gave you this, if I gave you like 400, 1.99, which is really close to 2, we agree? That would be a 99% increase, right? So 2 would be a what increase? 100. Yeah. It's how far away it is from 1, right? So, using that rule with exponential graphs, B is what? Zach is really hurting.
Oh, I thought you were like...
No, I'm old. That's all the only issue I have right now. Okay. B is what? Legitimately, here's what back. If B is between what and what, it's decreasing. 0 and 1, thank you. How do we know if it's increasing? It's greater than 1. So when we look at a graph of an exponential, what is this dashed line called? A horizontal asymptote. And it's on the x-axis. What's the equation of the x-axis? Y equals 0. And the great thing about 30-2 is it does not move because you can't transform it. Now, if we have an increasing exponential, I do something like this. And decreasing could do something like this. Gets closer and closer to that x-axis, but it doesn't touch it, right? What can we say about the x-intercepts? How many are there? None. I have an asymptote on the x-axis, right? Which means it can't touch there. That's the asymptote means the graph gets closer and closer to it, but it can't touch it. So exponential graphs in this form, y equals ab to the x, have no x-intercepts. If I want to talk about y-intercepts, when I hear y-intercept, what should I think immediately? X equals 0. So I can plug 0 into that equation, the y equals ab to the x equation, right? So if I go y equals a b to the 0, what is b to the 0? What is anything to the power of 0? 1. So what am I actually left with? just A. So it's 0 and A is my y-intercept. So if it's in the form y equals ab to the x, 0, a is your y-intercept, and it makes sense because if we look at all of these equations over here where I said I did word problems, this was the initial value when time is 0. This is the initial value when time is 0. This is the initial value when time is 0. The 400 and the 300,000. So those are just the y-intercepts, right? When time is 0 is when x is 0. So they're just the initial values, which is also known as the y-intercepts. We agree? So your a is always your y-intercept. We know that. What is my domain of every exponential? X such that x is none of the reals, because it's going to keep going on for life to the left and to the right. And what's the range? Y such that y is? Is it equal to? It's just greater than what? Because it's all up here. It's just positive. If I could say y is just positive, if I could just say y is just positive, I would be correct, right? If I just said y is just positive, I could be correct. How can I represent y is just positive? Y is greater than 0. That means just positive, right? Y-ER. Why can't it equal 0? It's the equation of my asymptote, right? That's where the graph can't exist. You can get closer and closer to 0, but it can't touch it, so we can't have an equal to sign. Then we're going to look at a log graph. If I give you log graphs, some people get confused and they're like, wait, there's a whole bunch of variables. I don't know what the heck it stands for. I want to punch it in my calculator so I can see it. Keep in mind, this is what I need to tell you, is if they give you y equals a b to the x like this, with a log in it, they have to give you some parameters of what a and b can be. They can't just let them just sit there. So keep in mind that b can't be 0 and it can't be negative. X can't be 0 and it can't be negative and it can't be 1. Like or it can't be just 0 or negative, sorry. So what we have to remember is that. But what they can do is they can say, okay, well, A is less than 0, B is greater than 1. And people will say, uh-oh, I can't type that in, I can't look at it. If they give you A is less than 0 and B is greater than 1, are we able to put in numbers for that? Yeah, and I try and not put in 1s, and I try and not put in 0s. So when it says A is less than 0, I'm going to say, okay, I'm going to try A equals -2. And then B is greater than 1. I could go B equals 2, but I try making different numbers. So I'm going to say B equals 3. Now can I type it in? Yeah, go type it in. Y equals -2 log base 3 of x. Type it into your calculator, into your y equals. And I want to draw your attention to this one again, because the graph looks like it's doing this. The graph looks like it's doing that. Does it actually stop there? No, what did I tell you? It'll keep going, but it's just getting so close that it's actually like fights it and can't draw it anymore. But it actually keeps going. So when you go to sketch this, you can input smaller x values and you will get y's that run along here. Now log graphs, this would be a decreasing log graph because it's going down from left to right. But log graphs have an asymptote that is vertical. And it's on the y-axis. What's the equation of the y-axis? X equals 0. Yeah. 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 Sure. You have to remember divided by log 3. Remember you go log x divided by log 3? Like you had to do this. Nope. Type it in like that, -2 log. Okay. All right. What's our domain? Yeah, x such that x is greater than 0. The only one that, when not a word problem, isn't XER. Linear is XER, quadratic is XER, cubic is XER, sinusoidal is XER, exponential is XER. Logs are not. Because the only part of the graph that exists on this calculator right now is greater than 0. Can't equal 0 because there's a dashed line. What's my range? YER. What about my y-intercept? Aren't going to be any, right? Because the asymptote's on it. So no y-intercepts. If I want to find the x-intercept of this one, when I hear x-intercept, what should I think? Y equals 0. So I'm plugging it into the equation that I'm looking at right now is y equals -2 log base 3 of x. So I said that it's a y equals 0, so I'm going to get 0 equals -2 log base 3 of x. I have to get x by itself to get my x-intercept. What do I have to do first? I thought someone said it. Yeah. Let's divide that initial over. 0 divided by -2 is 0. I have the variable stuck beside the log. If I have the variable stuck beside the log or in the base of the log, what am I going to have to do? Convert to exponential. Base of my log becomes base of my exponent, so I get 3 to the 0 equals x. And what is anything to the power of 0? 1. So it's 1 and 0. Then we're starting the next unit, which is probability. It has only 4 lessons in it, and it is the last unit of 30-2. When's your test on this? I'm posting the review that I said for logs and exponentials after this class. We have reviewed in the last 2 days everything from logs and exponentials except for regressions. But regressions are just 9 and 0, and we've done regressions a whole bunch of times. Okay, so experimental probability is one we don't really deal with. We deal with it, you guys deal with it in like chemistry and stuff like that. It's more experimental. But it's where you actually do what the probability is and then tell us what it is. So you flip a coin 10 times and you tell me how many actual heads came up out of 10. That's experimental probability. Theoretical probability is what we're doing for this whole unit. Theoretical probability is like, in theory, what would the probability be if I flipped a coin and I wanted to get a head on the coin? It would be 1 out of 2, 50-50, right? That's a theoretical probability. I could literally flip a coin 10 times and it never ever land on a head, correct? So it'd be 0 out of 10 for the probability. That would be experimental. We always deal with theoretical, like how much would it actually be if the chance of it happening. So here we have, in junior high, you were exposed to the following questions. A 6-sided die is rolled. What is the probability of a 2? So we're always going to do, up here it shows it. This is like the probability of getting a 2, and then this is the number of 2s over the number of sample space, or the number total. That's what we're going to do. So here, what you did was you'd go the probability of rolling a 2, and you'd say how many, the number of 2s. Thank you. over the number total. That's what you're doing each time. Now, the reason why I'm showing it like this, which you're never going to show it like that, is because when we start getting to more advanced problems, you're going to have to remember that that's what you're doing. You're doing the number of 2's, which is 1, out of the number total, which is 6. And here we have a 6-sided dice is rolled. What's the probability of rolling a prime number? What's the first prime number?
The ringer was on. I turned it on. I was making sure I was being respectful. Why was it on this whole time? Because it's on, because I was supposed to make the whole word Christmas.
Let's put right here. It's gonna. I'm home. Spend time with my chicken.
Okay, chicken down below.
Have eyes,
I was
but it's
worried.
okay. All right. Doesn't have to. So 6-sided die. What's the probability of rolling a prime number? What's the first prime number? I'm indirectly trying to show it to you. How many fingers am I holding up? If you see 1, go to your eye doctor immediately. Immediately. If you see more than 2, also go to your eye doctor immediately. I asked the question and held the fingers up in hopes that that would get you there. 1 is not a prime number nor a composite. Our first prime number is actually 2. 2 then. I'm no longer using my finger. I'm counting. 2 is 1. Then the next one is 3. What about 4? No. What about 5? What about 6? So how many are prime? 3. So that reduces to a half. And here it says a regular spinner is divided up into 4 sections labeled clubs, diamonds, hearts, and spades. When it is spun, what's the probability of landing on hearts? How many hearts are there? No. 4 sectors. This has nothing to do with cards. There are 4 sectors. There's 1 that's clubs, diamonds, hearts, and spades. How many heart sectors are there? 1 out of 4. Now we're flipping over. Two coins are tossed. Now I'm going to draw your attention to this. When 2 coins are tossed, the best way of actually talking about 2 coins being tossed is drawing a little tree diagram. So we do like coin 1. Coin 1 could be a head or a tail. And then coin 2, which we did this in fundamental counting principle. Now you're going to make a tree branch off of the heads and the tails. So coin 1 could be a head. And then coin 2 could be a head or a tail. If coin 1 is a tail, then coin 2 could be a heads or a tails. Remember I told you it's more like a shrub or a sideways tree, not like an actual tree going down like a Christmas tree. So then we have our outcomes. How many different outcomes do we have? We actually have 4, right? We have heads then heads, heads then tails, tails then heads, tails then tails. So when you can actually physically see the outcomes, it's sometimes easier to do the probability. Remember when I told you when we were doing the tree diagram and fundamental counting principle that you really don't have to do it with that because it's actually easier to just do the fundamental counting principle, but it's helpful in probability? Well, today's the day. So this one wants, what is the probability of obtaining 2 heads? So the probability of 2 heads. So whatever we ask for beside the probability of 2 heads, always goes on, the number of that goes on the top and total goes on the bottom. So how many have 2 heads? 1 out of 4. Now if you flip over your page, we're going to come back to this one in a second, but flip over your page, there's like a blank spot. You see that? That's where we're going to go. So 2 dice are rolled. What's the probability of a sum greater than 8? So we need sums of 2 dice. So on the next page I told you to flip. On the next page, there's like a blank spot. That's where we want to go. So I was doing the tree diagram for heads and tails. But when we're talking about outcomes on 2 dice, you always draw an array. So on the top, I would have 1, 2, 3, 4, 5, 6. And then on this side, I would have 1, 2, 3, 4, 5, 6 sides on a dice. Our array will represent all the different sums because they want sums greater than 8, correct? If I draw an array, I'll get all the different outcomes. I should do this. I don't know why I wasn't extending it. So how many different outcomes are we going to get? 36. 6 and 6, right? We're going to get 36. Now, this may seem time-consuming, but I'm going to tell you it's not as bad as it seems because there's a quick pattern when you start summing these up, right? Like this is going to be 1 and 1 is 2, 2 and 1 is 3, 3 and 1 is 4, so then 5, 6, 7. 2 and 1 is 3, 2 and 2 is 4, 5, 6, 7, 8. 3 and 1 is 4, 3 and 2 is 5, 6, 7, 8, 9. 4 and 1 is 5, 4 and 2 is 6, 7, 8, 9, 10. 5 and 1 is 6, 7, 8, 9, 10, 11, and 7, 8, 10, 11, 12. So actually setting the array up is the time-consuming part. Filling it in really isn't. But how many different blue outcomes do I have? 36, right? 6 and 6 times 6. Now, I want all the sums greater than 8. And if I had to do that in my head and be like, okay, 4 and 5 is 9, 5 and 4 is 9, so that's 2, and I'd have to do them all that way, I probably would miss one, right? But if you do an array, yes, it's time-consuming, but it literally takes all the brain matter out of the question. Like, it makes the question way easier. So, if we go here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of how many? 36. So we're going to go back to our page before so we can put the actual answer. So whenever I have like a 6 and a 6 die being rolled at the same time, I will draw an array every single time. Because I do not care how long it takes. So this is probability of a sum greater than 8. It's going to be 10 out of 36 reduces to 5 out of 18. So for these ones, I'm going to have you guys work on these. We're going to go through them quickly at the beginning of class tomorrow. But here it says, I want the probability of 4-letter names. Well, how many names are up there? 10. How many have 4 letters? 4, right? Out of 10. So that reduces to 2 out of 5. So that's what we're going to do for all of these ones. Okay, these are the word ones. Then we come down here to the cards. And it says probability of a 5. How many cards are there? There's 12. It even shows you here. How many have 5s? How many 5s, sorry? People think this is a 5. It's an S. 1 out of 12. And that's how I would do those ones. Okay? Not crazy. These are all questions that I'm asking right now are all junior high questions. We're just remembering how to do probability. This one wants 52 cards. What's the probability of drawing an ace? 4 out of 52. If only you could go back to junior high, wouldn't life be great? It'd be so awesome. This is like a whole unit you did on this. It was mind-blowing. Yeah. I think you did it for a few years, actually. Really drilled that spinner. If you're missing out on the spinners, here they are. Now, this, when it printed all wonky. Ignore that. This is just a spinner numbered 1 to 8, and it's spun once, so it's numbered 1 to 8. It's an 8-sided spinner. Like 1, 2, 3, 4, 5, 6, 7, 8. And pretend those are equally likely, like that they're actually split properly, because mine are a little wonky. And it says here, what's the probability of spinning an even number? How many even numbers are there? 4 out of, which reduces to 1 out of 2. So you're doing all the way up to 22. Go all the way up to 22.